So first of all, it's a thank you to the Institute of Sustainable Resources for inviting me to speak. And I suppose a small apology to all the rest of you. I am not of Professor Joel Calmo's stature, but I hope I'll give you a few things to think about and to, if you want to say, chew on over the next 20 minutes. I'll do my best to keep on time. So essentially, I feel that in a way, part of my role here is to do a little bit of scene setting, but also perhaps to throw up a few ideas that that may find themselves discussed later in the session. So I'm going to start at a very basic point with water scarcity itself. The concept of water scarcity was perhaps first discussed at some of the UN population conferences during the Club of Rome, and much of the discussion about whether the world could feed itself in the late 60s and early 70s. And then the famine in Ethiopia in the mid-80s prompted Malin Falkenmark to discuss water scarcity as a way of trying to anticipate famines of that stature in the future. Could we anticipate these things? And so I suppose one of the things I would like to write right at the beginning is I hope you can see that water scarcity as a concept, right at its outset, had a direct connection with food. The other thing I'll just point out, Malin Falkenmark proposed this water stress index, which, whether you like it or not, is the most widely applied metric to define what we mean by water scarcity today. And the diagram is a straight copy from her paper in Ambio in 1989, and essentially it's a water crowding. And she was wondering how many people could be served by 1 million cubic meters of water per year. And essentially, drawing evidence from the state of Israel, she argued that 1,000 people, before you moved into conditions of water crowding, 1,000 people could share 1 million cubic meters of water per year. You can invert that and then say, essentially, a per capita freshwater availability of 1,000 cubic meters per year per person. How would you define freshwater resources? Well, renewable freshwater resources were defined by mean annual river discharge. And at the time, there was a group in St. Petersburg who had been compiling observations. There were groups who were developing, at this time, global models. And the idea of, well, we could take fairly quickly data from observations or from models of river discharge, and we could reconcile them with, and that essentially, by the way, river discharge represents what we might call the blue water flux. So the net contribution of water to the land surface from precipitation after you subtract the evapotranspiration. And so these are defining it in terms of blue water resources. And again, population data exists. The UN has been doing this under its population division for some time, but taking those population data and an understanding of river discharge, you could fairly quickly begin to compute the number of people served by a particular amount of water, and therefore ascribe whether an area is water scarce or water stressed or relatively sufficient with respect to freshwater resources. Now, the connection to food is this. We recognize, and to this day, about irrigated agriculture accounts for about 70% of all global freshwater withdrawals. And so, when you think about it really, a water scarce area is one with an impaired or reduced capacity to irrigate. And if we're looking forward now, we might argue that's an area which would then have its pursuit of the Sustainable Development Goal 2 to end hunger, achieve food security, improve nutrition, and promote sustainable agriculture. We would argue that perhaps the inability or the reduced capacity to irrigate may in part promote food insecurity or impair, if you want to call it, food security. One important thing to note, a common misunderstanding. water scarcity is unrelated to access to safe water. And therefore, there is no relationship between water scarcity and whether or not people have water to drink. So that if you weren't aware of that myth, please be aware of it. This is some data, for instance, national statistics for countries across Africa. And you can see, for instance, just taking a couple of examples, you can see that per capita freshwater resources in the Democratic Republic of Congo are very, very substantial, yet less or approaching only 50% of the people have access to safe water. Let's look at Egypt. Much, much reduced, essentially a water scarce nation, yet it is approaching 100% or near 100% access to safe water. So there is clearly not a relationship between water scarcity and Sustainable Development Goal 6.1, but we might argue there's a strong relationship between water scarcity and Sustainable Development Goal 2. If we take up it comparatively, particularly in light of the Sustainable Development Goals, an area in which there's tremendous amount of development needs to take place, we look at in sub-Saharan Africa. Food production depends primarily upon soil water, what we might call green water, not liquid flowing water in a river or within an aquifer. We're talking about water that is bound to the soil or within the physiology of the plant itself. As a region, sub-Saharan Africa, estimates from 2000 suggest that only about 4% of its cultivated land was under irrigation. Compare that with, say, South Asia or Southeast Asia, where it is more like 40%. Or the global average, which is somewhere around 18%. There is a kind of an interesting consequence of that. It means, for instance, this water scarcity threshold of 1,000 cubic meters of water per year greatly exaggerates freshwater demand in places, for instance, in East Africa, where per capita use is typically between 20 and 25 cubic meters per person per year. So we're holding a region and declaring it water scarce, even though it doesn't need anything like the amount of water that, say, a semi-arid developed country like Israel does. Okay. Essentially, it's a very inappropriate metric. While we're on a bit of a critical streak here, there's some models here. These are the global hydrological models. These are some global hydrological models that have been used to calculate water scarcity around the planet. And I'll start with, for instance, the paper in Millie. I think this one is nice and clear. And if you look at the data, by the way, for those of you who are interested in this area, it's important to recognize that the plots that you're seeing right now are log-log. Okay? They're not linear, they're log-log. And essentially, where you see blue dots, it means the model overrepresents it by more than 50%. Where you see red dots, it means the model underrepresents it, okay, by half. Essentially, for the model published in Nature in 2005 by Millie, half of the river basins that they were trying to model, they either modeled river discharge at less than half of what is observed, or more than double what was observed. It's not very precise. If you look, the following plot actually shows a comparison of two global hydrological models, Water Gap and PC Glove WB. Again, if you're in this business, those will be familiar to you. And this is a plot from the most recent paper by Petrodol and the group. And the point being, these are log-log plots. And this is a comparison between the ability of those models to represent low flows and high flows. And you can see the Water Gap model does a fairly good job at high flows, but again, PC Glove not so well, and the other ones, again, even the Water Gap itself struggles to represent the low flows very well. I should say that Water Gap is the only one of the global hydrological models that is currently calibrated. Okay? So the global hydrological models that are being used to calculate freshwater resources on the planet are, with one exception, they're all uncalibrated. We really don't know whether those projections are correct or incorrect, or even the validity, how strong we might believe in them. So one sobering thought I would like to say is global water scarcity remains inadequately defined both by the models and by the metrics. There's a long way we can go to improving on this, and we could make some improvements comparatively quickly, I think. Clearly on the modeling front, people are working very hard to improve these models, and that will take longer, but certainly on the metrics, and I have a suggestion how we might move in that direction shortly. Well, let's look at how people have naturally adapted to freshwater, to water scarcity. And we can see on the left, of course, the use of canals. So drawing from water storage, taking water, you may know the canals themselves, where people have dug tunnels to allow water from higher pressure to flow naturally without the use of pumps from an area of higher water pressure to an area of lower water pressure. And clearly this is a way of redistributing water to areas of need, particularly for agriculture. Or other solutions are to store seasonal flows, for instance, in the construction of impoundment dams. And in fact, the World Bank has even suggested that reservoir storage could be equivalent to or reflect essentially development. Those with a very high per capita reservoir storage volume are developed, and those with a low per capita reservoir storage, they would argue would be comparatively undeveloped. And as I'll argue shortly, I think this is a rather narrow interpretation, and that there's a much broader perspective that might be considered. Essentially, if we look at how humans begin to disrupt, if you want to call it, or alter the terrestrial water cycle, the global water cycle, this is actually a focus of some significant amount of work by the modelers at the moment, beginning to recognize that the world is not a pristine place, and it has been substantially altered by human activity. And humans generally redistribute waters from rivers and aquifers to the land, and eventually to the atmosphere, through both irrigation and dams. And this, of course, is associated with energy production, and obviously recognizing the costs in terms of water resources associated with such energy production, and to regulate low flows. This is some work that some colleagues and I, led by Lala McDonald, the BGS, showed. And one thing just to indicate here is, in northwest India, for instance, engineering work from the 19th century all the way to present, and the digging of canals, unlined canals, across that area of northwest India has led to a very substantial rise in groundwater levels. So basically there was a century-long groundwater accumulation, and what we're looking now, associated with intensive use of groundwater for irrigation, is a depletion that follows a long-term groundwater accumulation. And this was achieved by basically people diverting water out of rivers into irrigation canals, and that acting as from a hydrogeologist perspective, a wonderful managed aquifer recharge system, where you're taking water out of rivers, distributing it around a landscape, and it leaks from those canals into the subsurface. Another thing we need to recognize, of course, is how humans also alter not only the quantity but also the quality of water resources themselves. And one of the things that we recognize in the Indo-Gangetic Plains and the Indo-Gangetic Basin, including both Bangladesh, Pakistan, and northern India, as well as parts of Nepal, is that the future constraints on water use in this area are actually not depletion or storage-based, but much more related to by volume due to quality. I would argue that actually we should redefine water scarcity not in terms of flows, but in terms of storage. And that actually where we run into problems is when we realize we have inadequate storage to meet an imbalance in flows. And anyway, I'll leave that for another. But the basic point about the storage here, the key point and where I would differ, for instance, from this focus on reservoir capacity, is you could look at storage in a much broader perspective. Storage not only associated with a reservoir, though that may be the case, they could be small scale, but also with groundwater, with soil water, rainwater harvesting from rooftop catchments. Storage does not have to be a large impoundment dam. It could be broad. The concept of storage needs to be broadened to both natural and constructed stores. Looking beyond reservoirs, substantial distributed natural groundwater storage exists. A big question is whether or not it's sustainable. Again, work with my colleague Alan McDonald at the BGS, we looked and quantified the volume of groundwater resources across Africa. And of course it was a first estimate, you might say, and all of this would need to be revised by more detailed local assessments. The basic point in showing you this figure is that the groundwater storage in many countries is 10 to 100 times the annual river flow of that country. And so you can see how a metric like the water stress index or other metrics that are based solely, on river discharge are inadequate because they do not represent actually the water resources that are maybe available to address water shortages that a country may have, and critically, that being storage. The question of sustainability is a difficult one because our track record so far is not especially good. In some of the major agricultural regions on the planet, the California Central Valley, North China Plain, High Plains Aquifer in the US, Northwest India, even in very seasonally humid Bangladesh, what we're seeing is groundwater storage decline. So there's a net groundwater depletion taking place in all of these locations. And of course, the situation in California, particularly last year, is one that made headlines in many locations. So, although the track record is poor, I don't necessarily mean it suggests that groundwater is not a suitable source of storage for addressing water scarcity, particularly in relation to water for food. I say that in particular because climate change is expected to have some important impacts on the hydrological system. Now, we don't know, and there's great uncertainty about where it's going to be wetter and where it's going to be drier. But there's one characteristic about a warming world for which there is much agreement. More frequent and very heavy precipitation events, and fewer light and medium precipitation events. The consequence of this is more frequent and intense floods and longer droughts. The consequence of those from a blue water resources perspective is an intensified need for storage, and I would argue groundwater dependence. The implication of this moves beyond just river and groundwater resources. More variable rainfall leads to more variable soil moisture, reducing crop yields, and increasing irrigation requirements. You either accept a reduction in your crop yield or you adapt and you draw water to try to supplement that decline in soil moisture through some kind of supplementary irrigation. There's an interesting bit of science that maybe many in the room won't be familiar with, so as a hydrogeologist I feel a bit duty-bound to explain. And that's that the intensification of precipitation as a result of global warming actually from a water hydrological point of view, from a water balance point of view, favors groundwater recharge, particularly in the tropics. So groundwater there becomes a kind of natural, if you want to call it hydrological, solution to adapting to this change, using groundwater to adapt to this change in soil moisture. So I focused a tremendous amount on blue water. Sorry, now there's a feedback echo. And so, of course, I knew that Tony was going to be here, and I knew that I would have to say a few words about this. And the bit is, can we trade ourselves out of water scarcity? Meaning, can we address water scarcity not through engineering and pipes, or even wells, although I may advocate for it? Can we trade our way? So can the virtual water trade, through movements of agricultural products and other commodities, and I'm sure most of you are familiar with these sort of numbers, about a kilo of rice or a kilo of maize. And I think all of us are familiar about these numbers. Oh, a particular debt to Tony for that. Now, can we address water scarcity through the importation of food from water-sufficient countries to water-scarce countries? So water-scarce countries no longer need to live under the label of being water-scarce because they no longer have necessarily the ambition to grow all of their own food, but to import it. If we look at the moment, this is some of the work done by Arjen Hoekstra and others, at where the virtual water trade looks like at a global scale. The green in this plot, if you're not unfamiliar with it, are areas where they have a net virtual water flow out, and the red are areas where they have a net virtual flows in. So you can see that here we are in Western Europe, particularly if we think of Germany, Spain, and the UK, in bright red. And we, of course, largely consume imported food now, rather than we are no longer anywhere near self-sufficient. But if you look at the details, arguably trade is more often from water-scarce countries to water-sufficient countries. I'm sure Tony will have a word or two about that, but that is maybe a somewhat superficial or casual observation from the data that are there. So I'm sure I've run out of time, so I'll just sum up and say a few concluding thoughts. The global water crisis is inadequately defined both by the models and the metrics. I don't necessarily mean go ahead and we need more research, but I think what I would like us to say is to have a humility about how imperfect our understanding of the global hydrological system remains in a quantitative sense, and at the moment how we keep applying comparatively inappropriate metrics to define that. And clearly, in case anyone was out, water scarcity is completely unrelated to access to safe water. So groundwater, as a hydrogeologist, I'm biased of course, represents both a key constraint to global food production, issues around depletion and quality, but also as a key opportunity to adapt to climate change. And although I think there is tremendous opportunity here in using the virtual water trade to address water scarcity, I suppose at the moment that ambition perhaps doesn't seem to be fully realized, and maybe there's ways of addressing that. I'm not an economist, evidently. Thank you.
Thank you.